Okay, today we're going to take a look at something a little bit new. We're going to go back and talk about polynomials some more. So first couple things, some definitions. So monomial, with mon meaning one, basically is just a single term. So x is a monomial, or 2t is a monomial. So it's a single thingy or a product of single thingies. 8y is a monomial. Polynomial just means that we have multiple of these. Man, I cannot spell today. So we're going to have a combination of these single terms adding or subtracting together. So x plus 2t, that would be a polynomial. Traditionally, when we look at them, it'll all be one matching variable. So x squared plus 3x plus 5, that is a polynomial. All right, so let's kind of talk about the big formal kind of ugly definition of them. So when we talk about a polynomial, we're really talking about something where we have a function and we have a set of coefficients and variables to powers. And we keep going down, having smaller and smaller powers until we're out of powers. I know that looks kind of crazy and ridiculous, but I'll kind of go over it here in a little bit. So when we look at this thing, n, that's our highest power, that tells us the degree of the polynomial. Our a sub n, which is the coefficient in front of that highest degree term, that is called the leading coefficient. Let's see. A naught, that last term, is called the constant term because it's the only one that doesn't have a variable associated with it. Let's see, we have some basic rules here. So all of our a sub n, so all of our coefficients, have to be part of the real numbers. So in other words, we can't have any I stuff, no complex numbers, but anything else goes. Roots are okay, fractions are okay, decimals are okay, negatives are okay. Just no I's, no complex numbers. And then all of our n's have to be whole numbers. So this is actually the most restrictive part, is when we're looking at those different n's. So when we're looking at the exponents involved have to all be whole numbers, 0, 1, 2, 3, 4, and so on. So we're not allowed to have any negatives, we're not allowed to have anything else. We can only have whole numbers as the powers. So quick example, if we had 3x squared plus 5x plus 2, this would be a polynomial because the coefficients are all real numbers. They're not imaginary, they're not complex. And all the powers involved are whole numbers. We have a 2, a 1, and a 0. So that would fit, it meets our two main criteria. When we go to talk about polynomials, we'll typically talk about types based on that n value. So if n equals 0, that's just a constant, literally 5 or 10 or something similar to that. N equals 1, that's going to be something like x plus 3, so that's a linear. N equals 2, that's a quadratic. So all of these should sound familiar. These are ones that we've talked about before. You talked about in Algebra 1. Like x squared plus 3x plus 1 would be a quadratic. N equals 3 is a cubic. So that'd be something to the third power, x cubed, dot, dot, dot. N equals 4 is called a quartic. If n equals 5, that is a quintic. And it kind of keeps going with some ridiculous names. But for right now, we'll just kind of worry about n equals 1 through 5. So now that we have some real basic information about polynomials, we can look and identify things. So let's say, for example, that we had x to the 4th minus 1/4 x squared plus 3. So first step is it a polynomial? All right, so to check polynomials, we look at the coefficients. All those are real numbers, check. We look at the powers. All the powers are whole numbers. So yes, it is a polynomial. If it's a polynomial, we can then take a look at the degree. So the degree being the highest power, so this is a 4. Type is just those matching fancy names from our previous chart. So a power of 4 is a quartic. Our leading coefficient is going to be the coefficient in front of the one with the degree 4. So this is a 1x to the 4th. So our leading coefficient is just 1. Let's see. Oh, and standard form. So standard form has to be decreasing order. So we always want to write it with the most important terms first, and those are typically going to be the ones that have the highest power. So for it to be in standard form, it needs to be the highest power, then the next highest, then the next highest, which in this case, it is in standard form. We're going from the 4 to a 2 to a 0. So yes, this is in standard form. I could just rewrite it to make it really clear. And that's the kind of information I might ask about for these. Let's take a look at something a little bit weirder, maybe 7x minus the square root of 3 plus pi x squared. All right, well, this is definitely a little bit stranger. So again, we go to check, is it a polynomial? So coefficients, 7 is a real number, negative root 3 is a real number, pi is a real number. So that checks out. Now we look at exponents. We have an exponent of 1, exponent of 2. That's good. Yes, this is a polynomial. Our degree is our highest power. That's this guy here. So our degree is 2. A degree 2 polynomial is a quadratic from our chart. Our leading coefficient is going to be the coefficient in front of that degree 2 term, which in this case is pi. And then writing it in standard form, again, we'd be putting it in order of the powers. So this would be pi x squared plus 7x minus root 3. And then we'd have it in standard form. All right, let's take a look at one more. How about if we had 5x squared plus 3 over x minus x? All right, so our first check is a polynomial. So we look at the coefficients, 5, 3, negative 1. Those are all real numbers. We're good. We look at the exponents. And here we run into a problem. So 2 is good. If we look at that term, that's the same thing as 3 to the negative 1, or 3x to the negative 1 power, minus x. We're not allowed to use any exponents that are integers. It has to be whole numbers specifically, so no negatives are allowed. So this fails. This is not a polynomial. And we can move on with our life. We don't have to go through and analyze all the rest of it. All right, now our next step is evaluating polynomials. I zoomed in kind of far today. So our first method of evaluating a polynomial is really straightforward, and it's honestly what we've done before. So let's say we had f of x equals x cubed plus 3x squared minus 4x minus 5. We want to evaluate it when x equals 2. That's literally just saying plug in a 2 for x and see what we get. That's all it means to evaluate a polynomial. So if we plug in a 2 for our x, that would end up giving us a 2 cubed plus 3 times 2 squared minus 4 times 2 minus 5. And we could go through and we could actually solve it. You could type it all into a calculator, get an answer that way. That's fine too, honestly. And it looks like we get 7. So I'm not going to do a bunch of examples of these. This is exactly the evaluations you've done in pretty much every math class at this point. What we're going to do is we're going to look at another method of evaluating polynomials. And in all honesty, I don't find it all that useful for the most part as just a tool for evaluating. The reason we're going to go over it is because it'll become very useful later on for something else that's related. So at this point, we're going to practice it in a nice, controlled, easy environment so you can get used to it. So let's take a look at this exact same problem, but we're going to evaluate it using synthetic. Sometimes it's called synthetic evaluation, sometimes it's called synthetic substitution in this case. Both of them are used they're almost mean the same thing, although not quite. There's a little bit of a difference. But we're going to synthetic evaluate this polynomial. So to do this, we have a very distinct process. We're going to take our polynomial and we're going to write down just the coefficients inside of a little bracket here. So we had a 1x cubed, so I put a 1, a 3x squared, a negative 4x, and then a minus 5. we have to put down every single one, even if there's something missing. So we have to have placeholders for that as well. So I'll show that as the next example. Whatever number we're evaluating as, we write it off to the side. This is now our synthetic evaluation procedure. What we're going to do is we're going to bring down that first number of 1, and I just write it down, whatever it might be. Every number down here, I'm going to multiply by this term. So 2 times 1 gives me 2. The columns, I'm going to add. 3 plus 2 is 5. 2 times 5 is 10. Negative 4 plus 10 is 6. 2 times 6 is 12. Negative 5 plus 12 is 7. This is our answer. Notice it matches up quite nicely. Some people find this method a little bit easier. I don't particularly care for it, but there's nothing wrong with it. You can use it all the time. Our main purpose is just to practice using this procedure because we're going to need it in a couple lessons. So let's try a different example, maybe one that has a hole in it. So how about we're looking at x to the 4th plus x squared plus 2x minus 8, and we're evaluating it for x equals 3. All right, so what we're going to do is we're going to take this polynomial and we're going to put it into a bracket, and we're going to use those leading coefficients. So we have 1x to the 4th, and here's our problem is that we don't have any x cubes in here. So it is a 0x cubed, and we have to have those place value holders. We have 1x squared, we have 2x, we have a negative 8. I'm going to take my 3, put it off to the side, and now we can start the process. So again, we're going to bring down that first number and then multiply. 3 times 1 is 3, we add our column. 3 times 3 is 9, we add our column. 3 times 10 is 30, we add our column. 3 times 32 is 96, and we add our column. So we would get 88 if we plugged in an x equals 3 into this. This is our basic pattern for synthetic evaluation. You're going to write out the polynomial using the coefficients, including any placeholders for missing terms. This is the biggest reason why people mess these up. You have to include the zeros for anything that's not there. Go through our process, and then we have our answer. So that's this is synthetic evaluation. All right, our next topic is using polynomials, basic operations. Addition, subtraction, multiplication. We're going to talk about division later on because division is a little bit uglier. So let's create two polynomials. X cubed plus 3x squared plus 2x plus 1. And g of x equals x plus 5. Keep forgetting I'm zoomed in. Okay, so if we want to add two polynomials together, this is our easiest one. We're just going to write it all out with add. We're going to put an addition sign. So we have x cubed plus 3x squared plus 2x plus 1 plus x plus 5. That's it. Now we just combine any like terms and we're done. So that's all that's going to happen when we're adding polynomials, is that we're just combining like terms. So we get x cubed plus 3x squared. We have a 2x and an x is a 3x. And then a 1 and a 5 is a 6. That's all polynomial addition is. We're combining them together, combining our like terms. Subtraction's a little bit trickier. Just in that you need to be careful when we do it. So if we're going to do f of x minus g of x instead, we'll take our f of x, and here's where it might be better to keep things in parentheses. Minus our g of x plus 5. If we write it out this way, it becomes easier to see that this minus, when we subtract that polynomial, is going to affect everything in the second polynomial. We effectively need to distribute this negative sign before we can combine anything together. So this would become x cubed plus 3x squared plus 2x plus 1 minus x minus 5. This is probably the biggest mistake I see people make when talking about polynomials, is they forget to distribute the negative sign across the entirety of the second polynomial. So make sure you're actually distributing that negative as you go along. If that had been a minus 5, we'd have a negative times negative would be a positive as an example. So make sure you do that step nice and clear and you don't make sign errors. Finally, now that we have this, we can just combine like terms like we did before. 2x minus x is x. 1 minus 5 is -4. And that would be my answer. Okay, multiplying polynomials comes, basically what we're going to do is we're going to do foiling again, but we're going to modify it a little bit. So if we go back way back in time to things like this, from Algebra 1 or from much earlier this year, and we had to multiply it, kind of the old acronym they always taught you was FOIL. First, outers, inners, last. FOIL is great, but it only works for 2 by 2s here. If we have anything more complicated, it's not a good mnemonic anymore. In essence, what we are doing is we need to take everything in the first term and distribute it to everything in the second. And that's how I'm typically going to approach it. So this x would then have to go to the x, plus x would go to the 1, plus 3 would go to the x, plus 3 would go to the 1. So each term in the first distributed to each term in the second. The x went to the x and the 1, the 3 went to the x and the 1. We can multiply that out and then combine any like terms and get our answer. So that's kind of what we did a long time ago. This is in essence what we have to do with polynomials, just that it could be much bigger. We could have more terms going on. So let's do one example of this the regular way, and then I know a lot of people like the box method that used to be taught, so I'll go ahead and show the box method as well. So let's say we had x plus 3 times something bigger, x squared plus 5x minus 6. Okay, we can't do FOIL. We don't have first, outers, inners, last. So we need to just distribute. So I'm going to take the x to each of them, and I'm going to take the 3 to each of them. So when I do that, if I just write it all out linearly, that would be x times my x squared plus x times my 5x plus x times my -6. There's all the x's. Plus 3 times my x squared plus 3 times my 5x plus 3 times my -6. I almost ran out of room there. So that did all of them. We can go through and combine them. So that gives me an x cubed plus 5x squared minus 6x plus 3x squared plus 15x minus 18. Finally, after simplifying, we just combine any like terms. We just have the 1x cubed, we have a 5x squared and a 3x squared, is an 8x squared. We have a -6x and a plus 15x is a plus 9x, and we have a minus 18. So this would be our answer. This is perhaps the most direct method of doing it. There are several ways that you can do multiplication of polynomials. You can set this up as an old school multiplication problem where you put them on top of each other, and then you went through keeping placeholders. That also works out just fine. Since people were asking me about the box method earlier, I'll write down the box. So in the box method, what we're going to do is we're going to write each of our things along the outside. And then I'm going to make a little grid pattern out of it. So on the inside here, all I'm going to do is I'm going to multiply the matching terms. So x times x squared is x cubed, x times 5x is 5x squared, x times -6 is -6x. 3 times x squared is 3x squared, 3 times 5x is 15x, 3 times -6 is -18. Now I can just combine these guys. If you have all of the proper terms in the right order, you'll be able to look at diagonals. If there were missing terms, the diagonals will not be quite as good, so you have to be careful with it. But in this case, we'd have an x cubed, we'd have an 8x squared, we'd have our 9x, and then we'd have our -18. Honestly, I don't care how you multiply it. Use the box method, use old school columns, write it out with distributing, whatever. You just have to be able to multiply. All right, our final thought is we're going to talk about kind of end behavior. So when we talk about the end behavior of a function, what we're doing is we're looking at what happens when we go really far away. What happens when we go all the way out toward -infinity? What happens when we go all the way over to +infinity? So that's basically what we're going to ask, is we're going to say if x is going to negative infinity, what happens to f of x? If x is going to positive infinity, what happens to f of x? So this is what end behavior is. Sorry. Is we're trying to say if we go all the way left, what happens to the graph? If we go all the way to the right, what happens to the graph? So I'll do a couple examples of that, and then we'll talk about what happens with polynomials. So let's go to our friend y equals x. If we were to sketch that, this would just be our linear equation going up at a 45-degree angle. It's kind of off there, but I'm just freehanding it. So we could answer, if x goes to negative infinity, if we keep going left, this graph just keeps going down. So f of x, because it's going down, is also going to negative infinity. If x is going to infinity, if we went to the right, then as we go right, it keeps going up, so f of x would be going to infinity. That would be our end behavior for f of x equals x. How about if we were looking at negative x squared plus 1? All right, if I were to sketch that again, it's moved up 1, it's an upside down parabola, and we'd have something, and that's a bad parabola, but we'd have something that looks like that. So again, I'm asking if x goes to the left, what happens? Well, as we go left, it goes down forever, so f of x is going to negative infinity. As we go to the right, as we go to x goes to infinity, well, this is still going down, so f of x is still going to negative infinity. So when I ask you for end behavior, one of the easiest ways to do it at first until you get a feel for them is just to graph them. Put them in a graphing calculator, put them on an online grapher like Desmos, and see what happens. And then that can enable you to answer. Now the weird thing with polynomials here is this was our order 1. This is our order 2. There's this weird thing where our n minus 1 is the number of times that it can change direction. And by that, I mean how often it can change going up or down. So y equals x is the first order, it never changed. It started out going up and it just kept going up. N equals 2 means it can change direction once. Started out going up, turned around and started going down. So our general shape for n equals 3, a cubic, let's actually switch it around a little bit so it's easier to see. So for n equals 3, our basic graph can look something kind of like that. It's going to change direction once, come down, then change again and come up. Now it doesn't have to change direction that many times, but it can. And it's always going to be an odd number. If we were to look at n equals 4 and you were to plot out some random graph of these, it would look kind of like a W almost. We'd get something looking like that. This same kind of pattern is going to hold true if we kept going. All of our odd patterns are going to look something similar to that with more and more changes. And all of our even patterns are going to look like this, but with more and more changes. So this would be an example of n equals 6. So just keep that in mind as we go along. It has a very distinct little pattern of changes. If I asked you for the n values, all we're doing when we look at n behavior is we're saying what happens when we get further away. We're not caring what's happening on the inside. That's something we'll talk about more next time. We're just saying if you were to graph this, sketch it out, what approximately is happening as you move along. All right, so when you work on the homework, take your time. It's not that hard of homework. We're just kind of reviewing. It's a lot of vocabulary, a lot of identifying terms, and we're seeing what's happening from there.